Hey everybody, welcome to the first ever shop talk. I'm excited to be in my shop doing this. Hope everybody can hear me. Put your hand up or type in if you can't hear or see me for some reason, but we'll go through a little bit of the housekeeping on what you can do if something breaks down on your end, but I wanted to show my little shirt here. So yeah, so the idea came to me, being a hands-on guy, I'd like to see how things work. I like to put it in my hand. I'd like to see it work. So I had this idea, maybe I could do a presentation from my shop. So we've been practicing for a week now, and the best way to do that, how we could do a live demo. And of course, as most of you probably know, trying to stream something these days sometimes works and sometimes it doesn't. So here's my plan is I've got a bunch of slides I want to go through first, and then we're going to go to this demo behind me, but I did pre-record that, so I've got it as it's just a minute and a half video at the end where I can go up and show you some things on that. So it might sometimes be a little jerky on your end, depending on your your connection speed and stuff like that, but let us know how this goes, because we'd like to keep doing some live demos, and if we have to change technology or whatever, we'll do that. So we want to get it to you. So yeah, thanks everybody for showing up tonight. We've got a great group here, and let me just go through a few housekeeping slides. So yeah, sometimes if it breaks down, if it starts to get jerky or pixelated or the voice goes wah, 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 sometimes just log out and log back in and you might get a better connection. The connection to the internet goes through all these different switches all over the country. So sometimes just logging out and back in, you get a better connection, and it'll work out better for you. And that's a tech support number for GoToWebinar. We lean on them quite a bit when we have technical problems, and so far they've been helping us out. Mary does most of the heavy lifting on the back end of these, so she's on board here tonight. It's going to watch questions and stuff, but thanks to my team for showing up. So yeah, we thought we'd schedule 4 of these and see how it goes, and those are the next topics we have coming up. We'll do it at the same bat time, same bat station every week, and we'll just keep going until you guys had enough of it. But I got plenty of things to talk about and share with you. So this is one of my favorite topics. I like talking about errors. So, and the other thing that Mary at the end of this is going to tally up and let us know what we raised today for the for a couple different charities that we selected here. The World Central Kitchen, which goes around, these are actually chef-made meals that they send out to hospitals, and they go all over the world when there's a crisis somewhere and help out. And then same with the Samaritan's Purse, they're actually helping in Italy quite a bit also. So that one kind of crosses crosses the ocean and helps out a little bit. So those are the first 2 we thought would be good to yeah, we're going to put up to $5 for each person that attends tonight. So and we'll pick a different charity every time and keep that going if we can. So, and our the owner of our company, Marco Caleffi, started this, and he donated a big donation to some of the local hospitals over there. In fact, we got a picture here yesterday of looks like a brand new MRI machine or something that one of the hospitals bought with the donation that he made to him. So he likes doing that. We like doing it, and I think it makes everybody feel good in these kind of weird times that we're going through right now. So. All right, let's get right into errors. So this is what I've got. I think we can do this in an hour or less. Like I say, there'll be a minute and a half video at the end, maybe a couple of them. I filmed a couple of them. If they look good and work good for you folks, I'll show a couple different ones, but I'll cover most of this with slides. These will be, at the end, there'll be like a post-webinar survey, and if you want these slides, you're welcome to have them. You just click on that, and we'll just mail you a PDF of the presentation. This will be archived on as a YouTube. That Mechanical Hub will have access to that, and if you want to watch it again or somebody else would like to see it, you can just pass that link along. So the different topics, yeah, we're going to talk about air, we'll talk about oxygen, we'll talk about pressure, what to avoid. The good news about air, it's a pretty easy thing to eliminate once you know the technology, once you understand the mechanism of how air gets in there, where it comes from, and where to put the components in the right order. So it is a easy to fix problem if you have it in the system, and we'll show you some of the tips and tricks for that. So I think it's important first to talk a little bit about air and understand, well, there it is, the little bubble right there shows what air is. I mean, it's mostly nitrogen is what's in the air, 21% oxygen, some inert gases, some dust or pollution, different things in there. But what happens is when we fill up a hydronic system, there's going to be some air in there. We're going to do the best job we can, purging the big bubbles. We're going to put isolation valves and purge valves, and we're going to get most of the air out. And then we'll get our circulators going, and we're going to start moving that fluid around, and it's going to have entrained air. It's going to have dissolved gases in there. We want to get all that out. And in a perfect world, what will happen is we'll get the oxygen out. And the way the oxygen leaves a closed loop system is it oxidizes any ferrous metals in your system. So if you've got a cast iron circulator pump, if you got some, steel nipples that you connect to the boiler with or whatever, those are going to oxidize. And once that happens, you should have what's called dead water. And dead water is like, well, you've heard of the dead zones in the Great Lakes in the summertime when there's a big algae bloom. It consumes all the oxygen along the shoreline of the lakes or wherever those algae blooms are. And then there's not enough oxygen in that water anymore to even support the fish life. So that's what they call dead zones. Well, the same thing happens in a hydronic system. You could get to the point where you have dead water. And if you have that, you won't have any more corrosion. If there's no oxygen in there, you're not going to have any more rust. That being said, it's really hard to keep oxygen out of a system. You can get into so many different places. I'm talking oxygen at the molecular level. And so, we deal with that on an ongoing basis by either putting chemicals in there. A lot of the hydronic chemicals will have a component, different brands use different components, probably a sodium sulfite, something like that, that absorbs any oxygen that gets in. But of course, you've got a chemical romance now, and you've got to keep adding those chemicals every so many years to boost up that oxygen scavenger to keep it out of there. So Mother Nature hates an imbalance of any type. If you've got high temperature in a building and you've got cold temperature on the outside, turn the heat off, and what's going to happen? Obviously, the building's going to get as cold as the heat's going to leave and the building's going to get cold. The same thing with humidity. Got a lot of humidity inside, humidity starved inside the building, high humidity outside, that humidity is going to come in the building. The same thing happens with oxygen. If you've got an oxygen starved condition inside a system, inside a pipe, inside a tube, Mother Nature is going to try and balance that out. And the way it happens in PEX tubing is it goes through the wall of the tubing. And it was hard for me to grasp that. Well, wait a second, I put 150-pound air pressure on this PEX tubing and it stays there for a week, doesn't leave, and you're telling me oxygen's getting in there? Yeah, it is. And we're talking oxygen at the molecular level. And you'll see here in the next picture how that works on the tubing and how they show you what's acceptable as far as oxygen. So it's an insulator. If we have it in our pipes, if we have it in our boiler heat exchangers, we don't have good heat transfer. So we want to get it out of there. We want to get it out of our radiators. We want to get it out everywhere. So let's look a little bit more about oxygen and corrosion. This was a really interesting book I read a couple years ago. If you'd like to read, certainly get this one. And it was written by an author who writes for Outside Magazine. And he looked at corrosion in the US and all the problems that it can cause. And he looked at the Alaska pipeline. He looked at a lot of different things. But one of the things he did was really interesting. He went to Can University in Golden, Colorado, a Ball company that makes canning jars. They also make, 1.3 million aluminum cans a year. When they make an aluminum can, you go to them and let's say you've got Eric Auni's energy drink, and you go to them and say, okay, I've got an energy drink. I want you to can or bottle this for me. And they'll analyze that drink, and then they'll build an aluminum can, and they put a barrier inside that aluminum can that, number one, protects your product from getting the taste from the aluminum, and also protects your product from eating away the aluminum can. So it was pretty interesting how they formulate all these different internal coatings for cans. And the same thing if you buy a gallon jug of milk at the grocery store, it's going to have an oxygen scavenger in it. And they're going to put a barrier in there, otherwise the product will spoil because the oxygen is going to go through, believe it or not, the wall of that plastic jug. So inside that PE, whatever plastic that jug might be made out of, there's going to be a barrier in there for oxygen, protects the product, keeps it from spoiling, and that keeps the taste of the plastic from getting to the milk also. So down here, this DIN standard is what we use in the industry, and this was developed, and it's been upgraded a few different times, but it basically says the acceptable amount of oxygen that can, now it's in metric units, that can go through the wall of a PEX tubing. And they do that at 40 C, and that's the amount there. Now, I don't know if that means much to you, 1 gram per cubic meters, but what's important about this to know with the PEX tubing is the higher the temperature, the more that oxygen can ingress in there. So if you run that PEX up around, even with an oxygen barrier, EVOH barrier, whatever it might be, if you run that up around 160 degrees, that oxygen ingress goes up quite a bit. It's 2.5 times higher. And we know that by if we do a high temperature system like maybe a fin tube, with PEX tubing, we tend to get more oxygen ingress in those. You'll see expansion tanks fail a little bit sooner. So you can't stop that oxygen 100% with just putting an EVOH barrier on. You can limit it, you can lower it down to a point where it shouldn't cause a lot of problems, but know that it does get through there. The only way to prevent it is use copper tubing. Oxygen doesn't get through the wall of a copper tubing. And so here's some of the issues. Obviously, if we have an air pocket somewhere in our system, we can stop flow completely. So if we go over a beam or something like that, this is where we can trap air. And of course, we stop circulation completely if we have a big enough air pocket like that. This example is an old picture that Heat Boy sent me years ago, and I know where this came from. This was on a non-barrier tubing system, and that pump, I mean, you can barely even get fluid through that anymore, and that was caused by the oxygen ingress on an ongoing basis. So every day, every month, every year, oxygen's going through the wall of that. It's eating away the body in there. It's eating away any steel component. The expansion tanks are turning into that sludge you see there. So that's air. This is oxygen, and of course, noise. You know, you can hear air going through turns and pipes and through radiator valves and different things, and obviously that's going to insulate some of the heat away. So need to get it all out there. We've got to get the big bubbles out, we've got to get the small bubbles, we've got to get the micro bubbles, we've got to get the entrained air. These are all different types of air that's within your system. So one of the ways that we get air out of a solution and get air out of a system when we purge it is pressure. And so the first thing you need to do when you walk into a mechanical room from this day forward is I want you to find a gauge somewhere on the system. And if there isn't one that you believe or trust, take a gauge with you, screw it on the boiler drain, have a good test gauge on your truck, one that, you know, maybe a stainless steel case with maybe a glycerin filled so it doesn't bounce itself to death in your truck, and keep that as your good trusted gauge that you can test systems with. And so what I want you to do is turn everything off, turn all the pumps off, turn everything off, and read that gauge, and that indicates the static fill pressure. That's the pressure somebody, maybe you, put in that system the very first day you filled it. And so what should that pressure be? Should it be 10? Should it be 12? Should it be 15? Should it be 50 pounds of pressure? What does the pressure have to do with it? Well, this little chart over on the side kind of indicates that pretty well. Is the amount of pressure that you put on the bottom of a column of water has to do with how high you can lift that water. So if I've got a 10-foot column of water, if I want to get water up to the top of this, I've got to put about 4.33 psi on the bottom of that to lift that up 10 feet. Now, if I had a building that was 12 feet tall and I only put 4 pounds of pressure on that, I'm going to have a big air gap across the whole top piping of that building because I haven't put enough pressure in there to squeeze that air bubble out. It's not the circulator pump that's going to take this little gap at the top of this out. Now the number is 0.433 psi, just under a half a pound of pressure to lift water up a foot. Now if you round that off to 0.5, you can do the math in your head. So if I've got a 30-foot tall building, I'm going to need 15 pounds of pressure to fill that building up. You know, it'll give you a little extra with the fudge on that, you know, conversion to 0.5. But in addition to filling this up, so if I put enough pressure on that to fill that all the way up to the top of where this air vent is, I'd like to have a positive 5 pounds of pressure at the highest point in my system. That could be the manifold upstairs in your bedroom closet or whatever the highest point, could be an air handler in the ceiling somewhere. And the reason I want to do that is with these little float type of air vents here, the way these work is the little float in there, when the fluid comes in, like in the picture, it floats up. Well, it's the buoyancy of the float that's shutting that little valve in there off. If we filled this all the way up and put a little pressure, now I've got a little pressure that's helping me make the seal at the top of this vent in addition to just the buoyancy of the float. So positive 5 pounds of pressure at the highest point in the system, just do the math and you can come up with that. Most of the time when you get a fill valve or an expansion tank out of the box, it's going to say pre-charged, typically 12 psi is what they pre-charge. Don't believe that. Sometimes that leaks out, sometimes they overcharge it. Always check your expansion tank before you put it into the system, but that's the number, and it would vary. If you're working on commercial buildings that are 40, 50 feet tall, you're certainly going to need more than 12 psi to fill that system up to get the air pushed out of that system and help you purge the system. Not going to be a sales presentation. I will show you some of the vents that we make just for the you know, just to know what's out there. So these are a lot of the different vents that you'll see out there. These are typically auto vents, we call them. A little float in there, just floats up. Air's in there, float sinks, water comes up. Different sizes, different connections. You can get different accessories. There's some manual air vents that we make, some little hydroscopics, repair kits. Now, when you go and you buy a vent like this, there's a couple numbers that you'll see on all the air vents. There's going to be the amount of air that it can remove. That's usually in a CFM rating on it. So that's the amount of air that can actually come out of that vent when it's working. There's going to be an operating pressure, and most vents are going to be 150 pounds. So that means you could put up to 150 pounds static pressure on this vent. There's also a working pressure, and our vents, like some of these are 75 psi, we make some 90, I think we make a 120. We make a couple different working pressure ratings on these vents, and what that means is, let's say this one, and I think it is, a 75 psi working pressure. If I had a high head circulator or something in that system that can develop 75 pounds of pressure, this vent isn't going to let air out after 75 pounds of pressure. The vent's just going to be jammed all the way up against its seat, and you're not going to get any air out. So if you have a system that can develop that kind of delta P in it, either from the pump or the height of the building, you want to make sure that you've got an air vent that's got the higher pressure rating. So again, if I had a job that was developing 75 pounds of pressure, either because it's a tall building or I got that much delta P, I'd probably want to look and make sure I've got at least a 90 PSI working pressure air vent on it. Most of the work that we do in residential, the 75 PSI are plenty of working range on that. But if you do get into commercial work, if you do get in those situations, just know if you got an air vent, you put it on there, no air ever comes out of it, you probably got the wrong air vent and it's just jammed up against the shutoff and it's not going to let air out until you drop the pressure way down. And we'll talk about some of these other accessory items that we make that can be added on vents to really kind of enhance the performance of them. Watch my time here. Yeah, I mean, shout out if you have a question as we go here. I'd just as soon answer them when we're on the slide if you want. So,
can I read it?
Is there anything out
Bob,
there?
yes, I've got a question from Daniel Leary, and he is wondering about the dead water. Does that turn the white PEX piping gray?
Yeah, I guess I'm not quite sure what he means. I mean, dead water just means it's water that's been starved of all its oxygen is out of the water. So
Does it turn the pipe gray?
Oh, does it turn? I see what you're saying. What turns the pipe gray is when you do have oxygen in the system and whatever it's oxidized. Like if I put a brand new circulator pump in a job and I came back 2 days later and took the Allen bolts out and put it out, it's going to be gray in there. Or maybe if it's had enough oxygen, it's going to be red, rusty color. It's that gray coming off that cast iron metal that gets into that tube. And, you know, probably a year after you put the manifold in with all those little sight gauges to adjust the flow, you can't read them anymore because the water's turned gray. It's pretty hard to stop that. You know, if you put a chemical in there from day one, maybe had a blue tin in it, like what I've got in the system behind me, you might keep that water clear, but you know, it's going to pick up any solder flux, any pipe dope, anything that's in that system. It's really hard to keep a system perfectly clear of water in it. But yeah, that gray color is an indication of there's been some type of corrosion has gone inside there. Now, one way you can stop that from happening is pipe your system with all non-ferrous metals. You know, stainless steel, copper tube, stainless steel pumps, stainless steel expansion tank. Just like we would if we come across a non-barrier tubing system, we'd probably turn everything in that system into a non-ferrous metal so we don't have rust, we don't have corrosion, we don't have expansion tanks and all those components failing on us. So yeah, thanks for that question. That's a good question.
And Bob, I've got another question from
Bill.
Excuse me, Bill, if I'm pronouncing your name incorrectly, but Bill D'Agostino. If you had an air vent that was set to 75 PSI,
yep,
but your system routinely went above 75 PSI, would it not only not work, but would it lead to a shorter lifespan?
That's a good question. I mean, it definitely wouldn't work, but you know, if you look at the mechanism, maybe I can point to it here as we look at that. Basically, what will happen is this little needle in here, which I've got an example, one of those right here, is just going to be jammed up against the seat. And so probably the best place for that air vent to have a long life is never work at all. Take it out of the box, it's always in the closed position. So as long as that needle valve isn't opening and closing a lot, it's probably going to last a long time. But yeah, unless you're going way over the working pressure range, I don't think it would damage anything up on the top end of that. You'd have to have a lot of squeeze to ruin this little. I'll just show you what's in there, at least on a Caleffi, and I think all the air vents are similar, but it's not unlike what you see in a Schrader valve. It's just this little stem that goes against a little O-ring in there and makes the seal. I'll show you a cutaway of that coming up. So yeah, the key is get the right vent for the application. Now, there's a couple things that I learned, which I didn't know my whole career as a plumber, almost 40 years now I've been doing this, is this little picture here. So what happens on this cutaway is when this vent is filling up with, air first, air is coming out, and the water gets up to this point right here. That's the point where that float's going to float up and it's going to shut that needle valve. And notice there's about a ½ inch of, I call it a head space or an air gap in here. And so all my career, I would go and take my little Tekmar screwdriver, whatever I had, and I would push this little valve down and I would just hold it down until water spit out of there. That told me, well, whatever this vent's on, a tank, a manifold, a boiler, whatever it is, I know I've got water filled up into my vessel, up in my boiler. Well, you don't want to do that because this little head space in here, that's designed to be in there to protect this little needle. Because if I held this down, and let's say I've got Teflon tape, I've got sawdust, I've got whatever debris in my system, and I hold that valve down, immediately I suck all that debris right in this little needle valve right here, and you might have an air vent from the day you put it in. It drips, or sprays, or squirts, or whatever, and that's because you should have left that little air gap in there to make sure that I didn't have the crud going right up in my valve that might be floating up in that water. Now, if you do want to burp an air vent, I would just loosen it on the thread right there until water comes out. Just loosen a thread or two. You see water coming out, tighten it back down. Your system's filled up to that point, and you don't have to push that needle valve in and lose your little air gap that's inside there.
Bob, I think you triggered a nerve because we have more questions.
All right, that's what
now,
we're here for.
I am going to open the mic up for Todd
Okay.
Landon. He's got his hand up.
Okay, let's
Todd,
try it.
perhaps you'd like to ask the question directly to the boss himself.
So like boiler water treatment.
Yep.
And the air vents. So you notice that the new condensing boiler manufacturers are really wanting us to put boiler water treatment in.
Yep.
And I've been using it for a few years.
Mm-hmm.
And I just want to make sure that, is there a recommendation for boiler water treatment?
Well, I mean, there's a lot of different brands out there. I mean, I have a favorite brand just because it's made in my local town here that I've liked, and I've worked with those people a little. I think any of the name brands, the key, here's two keys about putting boiler chemicals. And the very first thing you should do, even on a brand new piping system, is put a cleaner in there. I would just fill it with whatever's water is available on the job site and put a squirt can of that cleaner. And everybody makes it now in those aerosol cans, Fernox, Romar, Sentinel. And the cleaner is going to take out your pipe dope. It's going to take out your solder flux, which is zinc chloride. You certainly don't want zinc chloride in your stainless steel boilers. So get all that stuff out and then fill it up with good water and then put your conditioner chemical in with good water. Now you might have good water on the job site. Just check the pH, check the TDS, check the hardness of the water. If it's within the spec that the boiler manufacturer tells you, put it in there and then put your chemical in, and that system should be good for years and years and years. Now, most of the chemical people will tell you, go back in 2 years and just take our little test kit. Some of them have strips. There's different ways you can test it and test it. If the pH is plunged way down, you've got a problem. Something's going on in that system. If the hardness or something's gone up, it might mean you've got a leak and it's been taking on water that you didn't realize. You got a pinhole leak in it somewhere. But that going back every couple years and testing, it's going to be an indicator whether you've got it sealed and it's in good shape. But here's the thing about the chemicals that we put in there. There's about 4 key ingredients in those hydronic conditioners. There's going to be an oxygen scavenger, so that residual oxygen that you didn't get out when you heated it up and purged it out and oxidized your metals, it's going to have probably a sodium sulfite in there. Again, different chemicals are used for that. It's going to have a pH buffer, so it's going to buffer your pH up to a neutral range so we don't have aggressive water, we don't have too alkaline water where we start coating things out. It's going to have a film provider in I've got to cut away a pipe here somewhere. A film provider, it's almost like if you got inside a brand new piece of copper pipe and somebody took a magic marker and just put a thin coating on it. The film provider that they put in the chemicals just puts a very thin, a couple micron thick coating, and it protects your metals. If you rust, so to speak, or put a coating on the inside of your copper, inside your stainless, inside your aluminum boiler, whatever it might be, it's going to protect that metal. So if you do have aggressive water, if you do have aggressive glycol goes in there, it doesn't attack the metal. So you got an oxygen scavenger, you got a pH buffer, you got a film provider. There's a little bit of lubrication in there for your pumps. I work with Romar here in town, and they tell me there's 27 different components that they have to put into their hydronic conditioner so it can work with copper, works with stainless, works with aluminum, works with all the multi-metals that we have in your system, which is why they cost so much. There's a lot of stuff that goes in those, but I'm a big fan of good water and water treatment in the system. I think it just gives you the best longevity for all the components in your system, like to have good water quality, and that's clean the system, good water, then put your chemicals in on top of that.
Bob, I'm going to ask you another question.
Okay.
Did I lose it? I'm sorry if I did. Do air vents, this is from Andrew Roberts, do air vents have a hysteresis band, i.e. if a vent is at approximately 520 kPa, kPascals, I don't know, what does it reset at?
I think you're talking about on the valve mechanism here, what the range on the, I guess, hysteresis or differential on that. I mean, obviously when the float goes down, this is wide open. And then again, the operating or the working pressure is how much it can shut off against. But there's not really a range in there. I don't know if Kevin, our product manager, is online. If he can think of something that I'm not answering correctly on that, Kevin, jump in or something like that if you understand that a little bit better.
No, not really. I think, Bob, when there's enough air, that float will sink just enough to pop open that little needle valve. I don't think there's any kind of a built-in hysteresis. The needle valve will seat against that soft seal. So there's probably a little bit of
band in there.
I don't know, maybe some sort of a dead band, but it's really negligible, and it's not something that is measurable, I'm sure.
Yeah, and I'll ask the engineers in Italy if they've heard of that or know that. It sounds like you're working on metric units if you had that number there, so maybe I can find out a little bit more and we'll pass along if I do learn something, because I like to learn stuff too. So yeah, in the picture again, just cutaways of how these work in there. We have different versions of that. We've got a vertical version and stuff like that. But let me get into a little bit more of the meat. Unless you got another question there, I mean, shout them out anytime.
Bob, we actually have a million, but I'm going to ask you one more from Jared Gluck, and then at the end, perhaps we'll have a little bit more time, but in the interest of time. So the question is, you said to keep the system without non-ferrous metals if you don't want to have discoloration in the water. Yeah. So is stainless steel a ferrous metal?
Well, it depends on the grade of the stainless, and actually the 300 series of stainless, 304, 316, can actually get a little corrosion on them. I just read that. I was actually researching stainless steel that's used on the outside of buildings where they put some of the facade, or they make those balusters and parking lots sometimes out of stainless steel. The 300 grade, they tells me, can get a little bit of corrosion and get a little bit of rust spots on it. And I actually, in one of my trucks years ago, I had some stainless steel on the toolboxes, and I would get these little pit marks. It depends. There's a lot of different grades of stainless. The 400 series actually sticks to a magnet, and when I do the demo on this, I'm going to put some 409 stainless chips in there because they'll stick to my magnet, but they won't rust my piping and stuff. So it does depend on the grade of it. But again, if you've got the conditioner in there, it's going to coat that out, and that metal won't get those little rust spots or pockets on it. Different manufacturers have been trying different stainlesses over the years. Indirects used to be 316, and they went to 304. Some of them now use 316 for the shell, 304 for the coils. Some of them are using 409 for the coils. Every grade of aluminum has different properties. Some of it might weld better. Some of it might take expansion and contraction better for the coils where they get hot and cold. So I don't know that anybody has the perfect stainless. Some of them use a TI, titanium stainless. Viessmann tends to use a TI, which is a much more expensive grade of stainless where they put titanium in it. There's an AL series out there, which is Allegheny Aluminum, is a company back in Pennsylvania that has a special stainless grade that they make that's supposed to be a little bit more resistant. So yeah, it depends on the grade of stainless, but it certainly can get those little rust spots on it if it's a lower grade, doesn't have as much nickel or chromium in it. Anything else, Mary? You want to keep rolling?
Well, why don't we keep rolling? And if you can be patient, we'll try to get to those questions a little bit later in the presentation, but in the interest of time, we'll try to keep moving here.
Yeah, and some of them we might answer as we go along too. So what I want to show you here is just, most vents are made this way now, but the thing of it is when a vent leaks, if it's dripping, if it's spitting, if it's spraying, something's stuck in there. So just take the cap off, and most of the time, right there it is, you're going to see that Teflon tape shard in there. You're going to see a little, if you reamed your copper tube and some of those shavings got in there, most of the time you can get the cap off this and get in there and service it and put it back into a working condition. Now those can get ripped in there sometimes, that little O-ring, if something sharp in there can damage it, or I suppose after 20 years they can dry out a little bit if they've never had water up there. But if you've got a new vent and it's leaking a little bit, don't be afraid to take this cap off and get in there and try and service it. We do sell just the cap as a replacement part. And another thing that's good to put on an air vent are these little service check valves. And basically that, when you screw this into that, it pushes open this little seal here. And so now if you have to take this apart someday to clean it or service it or replace it, you've got a little shut-off mechanism. I really like these. The only issue I have with these is we sell them to people, and I don't think the next troubleshooter comes and knows what that is. He looks at it and he thinks it's just maybe a thread adapter, doesn't realize it's a valve in there to make it easy for him to take it apart. And they tend to sometimes take it apart at the wrong connection at this thread here, not realizing maybe we should put a label or sticker on it and say it's a service check, not a thread adapter. But it's a handy thing to put on your air. All air vents are going to leak. I mean, I'll be honest with you, it's not a matter of if. it's a matter of when. So just make it simple to be able to, for the next guy to be able to repair it or service it.
Bob, we have, I'm sorry to interrupt you, but we have a hand up. So let's invite Gerard the Bros. I'm going to unmute you. Whoop. Gerard, if you unmute yourself, you can ask Bob.
Yeah, let's talk.
There you go, Gerard.
How these air vents work with the glycol?
Yep. All of our, I mean,
Instead
I'm
of
speaking
water.
for my brand, we accept up to a 50% of glycol, and that could be ethylene or propylene. And we don't like to see ethylene used, but sometimes we know in bigger commercial buildings, EG is still a viable fluid. It's actually a better heat transfer fluid, but no, they're rated up to 50% on pretty much all of our products, really, air vents or zone valves, whatever it might be. I would think other brands are rated for that too.
Okay.
The problem with glycol is when it goes bad is when it gets ugly. I mean, if the glycol goes bad, it turns to acid. Glycolic acid is what you have, and the pH drops. Then it can get more aggressive towards metals and seals and stuff like that. Usually, if you've got a glycol job that all of a sudden starts seeping out of joints here and there, check the pH on that, and there's a good chance that glycol has been stressed, and it's time to either flush it out and replace it or boost the, you can put inhibitors in. If it doesn't get real bad, you can boost that pH back up in the, you know, the 9 or 10 range, but at some point the glycol needs to be, you know, we had, if you guys are interested, we had a really good speaker on, I don't remember, Mary, when that was, one of the guys from Dow Chemical did a glycol seminar for our coffee and Caleffi, and I learned a lot in the hour about glycol, about, you know, what causes it to go bad, how you fix it, and different things. So if you want to go to our YouTube station, look up that, I think it was just called Glycol, and it was Kevin Connor from Dow Chemical that did the presentation for us. So here's a job that had a little, just a manual type air vent on it, on this bleeder L and this fin tube here. Obviously it's been leaking. So this is the little vent we make. This is a hydroscopic vent, and it's a manual vent. If you turn it in one direction, you can just bleed out your circuit there. And then when you turn it the other way, it's an automatic vent, and it uses these little fiber discs in there. So when the discs are dry, the air can come through and it'll vent out. As soon as fluid hits that, within 2 seconds, these will swell up and shut off. So it doesn't have a needle and a valve stem or anything in it. This is the shut-off mechanism. So some people like it because it doesn't have a valve that can get plugged up. Now this is a little ball check that allows you to take this out and replace it someday. When you pull it apart on this thread right here, this shuts closed and you can replace the cap. We say about every 3 to 5 years you might have to replace that, but sometimes this is a nicer vent on a dirty system, and you can see that's what Jason did here. I hope this isn't his skid mark from laying down his torch or something on that carpet there. But yeah, thanks for sending us a picture. We like to see how our product's being applied, and that was an example of an Instagram picture that we asked if we could share on the presentation. So a couple problem solvers. So what can happen on an air vent, and I'll show you where this happens in a couple slides. If you pull a negative pressure condition on an air vent, air can come into an air vent. So if you've got a customer that's got a chronic air problem, they call you up and they said, listen, I've had 20 plumbers over here over the last 10 years. They bleed the air out of my system, and 2 weeks later, I got noise, I got air, I can't sleep at night. How come nobody can solve this problem? There's a good chance somewhere in that building, somewhere in that piping system, he's got an air vent that's allowing air to go in the system. And that happens if you put an air vent under a sub-atmospheric condition, under a vacuum, under negative pressure. I'll show you where that happens in a system. So we thought about that, and we said, you know what if we made a cap? This cap right here is a check valve. It lets air come out, but it won't let air go back in. So you could take the regular cap, whatever might be on your air vent, and screw this on. Now air can still come out if you got an air bubble in there, but it won't allow air to get sucked back into there. So you can fix a problem that's been in a building for years and years that nobody understood what was happening. Now, know that you're treating the symptom, not the problem. You should go back to that job in the summer when you can drop it down, and I'll show you why that's happening in a couple slides. This will just fix it in a short time until you can go back and correct it, but know that we've got that little check valve. They're not very expensive. It's nice to have in your glove box for that, that chronic air problem that nobody else has been able to fix. The cap in the middle here. Yep.
Oh. Go ahead, Mary.
Okay, well, take a breath for one thing, and then I've got a question here from Steve Weiland.
Okay.
And he is wondering if can a microbubble absorber cause an air vent to pull air in?
Yeah, we're getting to that. That's a great question, and that ties into with what I'm saying. I've got a kind of a visual of that coming up in 2 or 3 slides here. That's Yeah, that's an important thing to know, and that's kind of the gist of this whole topic is how come I've got a chronic air problem on the system when I put in all the high dollar components, I've done everything right, why do I have a reoccurring air problem? And again, corrosion because of an oxygen ingress. So give me a couple slides, Steve, and we'll get to that. Hope everything's well with you.
And we have one hand up as well from Jeff
Oh.
Haskey. Jeff, I'm going to unmute you.
Okay.
You are self-muted, Jeff, so if you want to ask that question, it looks like he isn't. Are you there, Jeff? Okay, we're going to move on.
Yeah, you have a little microphone next to your name, and you got to click on that, and that'll unmute you. We can't do that from this end. You got to unmute yourself. We can open you up, but you've got to unmute yourself. So if you want to try again, we'll try it. If not, type it in, and we'll make sure to answer your question. So where was I? So in the middle here, this is a hydroscopic cap that can go on any of our air vents. And all we did is we put a stack of those fiber washers in here. And this is really nice. If you're going to put an air vent in a critical location, like maybe in a ceiling, a drop ceiling on an air handler, a manifold up in somebody's closet over a hardwood floor, this is a second protection mechanism for this vent. So if someday something gets stuck under that little needle valve I just showed you, this cap is going to catch whatever comes through there and it's going to shut it off. So it's a nice thing. We sell, some of our wholesalers buy all their air vents with this extra hydroscopic cap. And these are the little service check valves. We've got those in 1/8 inch, 1/4 inch, 1/2 inch that you can put on any of our vents. So think about this. I could take just a basic old vent. I could put a service check on it. I could put an anti-vacuum cap, and I could actually put the hydroscopic cap on the top of my check valve. And now I've got 4 functions in this simple little auto air vent. I've got a check valve. I've got the check valve here. I've got my service check. I've got this check. I've got the air vent that works by itself in here. And I've got the hydroscopic. I've kind of got a 4-in-1 device, which I think is the next picture. So that's what it looks like with all the components. We're going to give one of these away. We're going to have a trivia question towards the end here, but there's a service check, the anti-siphon check valve cap, and the hydroscopic cap. And by the way, this will fit on a lot of other brands. Most of the air vents now that you see out there, Watts, Take, or whatever, are made in Italy. They are made with that same metric thread on there. The only one I found that this doesn't work on is the old, the Made of the Mist, which has just a regular tire Schrader valve type of stem on it. It's not a metric thread, but pretty much all the brass air vents out there are you know, made in Europe, made in Italy, made somewhere there, so they're going to be metric thread. With that in mind, here's an adapter that we sell. You can find these on McMaster Car. I think Taco offers them too. It turns that metric thread, which is what, about a 6 millimeter, into an NPT, and now you can put a tube, you can put a hose on it, you can put an adapter on. And why you might want to do that, this is probably one of my favorite slides here from up in Canada. A lot of the boilers, if they don't have an air vent built right into the heat exchanger on the boiler, they're going to send one with the boiler, and we supply a lot of those to OEMs, and they're going to say, put a T on the top of the boiler and put that air vent up there. So as we fill these IBC boilers, that air vent's going to make sure the air comes out of that heat exchanger, and we've got a, you know, the heat exchanger full of water instead of air bubbles in there. Well, if you look at what this installer did, he put adapters on there and he put a copper tube off of every one of those air vents on the top of these boilers, and he's taking it down to the floor, just knowing that someday if that vent discharges, guess where it's going to go? Probably on your microprocessor, probably on your inducer fan in there, and now you got $1,000 repair instead of just an air vent. He's done that on all 3 of these boilers, and here's our big hydro separator, and the same thing, he's got a copper tube on that. I don't know, maybe they go to a drain. I can't quite see where they all end up, but at least it's not going to run down the side of the equipment when it does just charge someday. And this actually, this boiler is sitting right behind me here, this little Lochinvar Knight, and it had a little 1/4 inch. I put a nicer vent in it. I put the service check valve there. I got the hydroscopic cap on it just so I don't make a mess inside here someday if that vent does leak. So here's what's going to happen is every time a burner starts up, you're going to get a flame temperature, you know, random numbers here, let's call it 1800 degree flame temperature. The wall temperature, that metal, the stainless steel on the outside of the coils of this little Gianomi type of heat exchanger, again, it varies a little bit. They're going to see a wall temperature somewhere in this 300 degree range. So every time that burner comes on and that metal gets hot, these little micro bubbles are going to form. And an indication of that is take a saucepan out of your cupboard tonight, put water in it, put it on a burner, turn the burner on, and within seconds, you're going to see little bubbles are going to start forming on the bottom of that pan, and they're going to rise up to the top. And they're going to do that every time this boiler starts up, unless you have a device that gets these out of the system. Because here's what happens with air in a system. When I raise the temperature of water, I'm going to drive these microbubbles out of solution. If that temperature in that boiler goes back down to room temperature, when there's a no heat call, these little bubbles are going to be reabsorbed into that water. They're going to go back in the solution. Every time you heat up and cool down, heat up and cool down, these bubbles are going in and out, in and out, in and out. So you need something that as these bubbles start moving through your heat exchanger and we get them back to your air purger, I need a device that gets, and some of these, when I call it a microbubble, you don't even see. They're so small, it looks like cloudy water, which we'll show you when we get the demo going here. It looks like you got a blender going on in there. Those are tiny little microbubbles, and you need to get them out of there. And there's only a couple devices that can do a good job of doing that. Just know if you have high temperature applications, we do make some solar rated. These are rated for operating temperatures of 360 degree, 320 degree, 320. So if any of you guys are doing solar work, you should use a solar rated, because a regular 215 degree air vent's not going to last very long up on the roof on a solar array that can get well over 300 degrees. All right, if you leave this seminar with one piece of information, I want you to understand the concept of pumping away and why it's so critical to everything we've talked about so far for air elimination, for happy pump operation. So I would highly recommend you get Dan Holohan's book and read about it. I'm going to give you just a thumbnail sketch of what pumping away means. Wherever you, the guy that puts the system together, connects the expansion tank into this loop of piping, let's just call this a loop around a building, whatever it might be, wherever you physically make that connection of the expansion tank into the system, you develop at that point exactly right there, the point of no pressure change, PONPC. That's the only point in this system that this circulator pump can't change that pressure. If this is a 12-pounder, what do we got here, 10-pound pre-charge on this tank, and I fill this system 10 pounds of pressure, this circulator can't change that pressure right there. Now notice I've got a little bit of droop. If I've got a foot of piping here, even a foot of pipe has some pressure drop when flow's going through it. So I'm showing if I had a gauge right at the suction of my circulator, I'm going to read about 9 pounds because I drooped a little bit here from that point of no pressure change. Now, if I could put the expansion tank exactly there, it's going to be 10 pounds of pressure. So I went around, I piped this, I put a gauge at every corner of this circuit as I went around here, and I filled it up to 10 pounds static fill pressure. So every one of these gauges is going to read 10 pounds of pressure. Now I'm going to wire this up and I'm going to plug this in, and let's call it a 007 since it's green. And as soon as I plug that circulator in, it's going to increase the pressure on the discharge side of that circulator. How much? Well, it depends on the type of circulator. It depends on what this piping circuit is, how many feet of pipe, how many fittings are in there. But let's call it 8 pounds of pressure differential. And that's fairly typical on these little wet rotor circulators. I mean, 6, 8, 10 pounds of pressure differential. So notice every gauge in the system is jumped up in pressure because I've just added that differential pressure that the circulator, by the centrifugal force, has added to that system. Now, as I start going around my circuit through my pipe, through my elbows, I drop pressure. I'm down to 17 pounds here. I'm down to 13 pounds. I'm down to 11 pounds as I come around the last bend. Still at 10 pounds of pressure here, even though the circulator is running. So the circulator adds all its pressure as a positive. So let's change one thing in this drawing right here, and let's move that point of no pressure change to the other side of the circulator. And you're going to see this on jobs when you walk into them from this day forward. Look at where that expansion tank is not physically located. I don't care if it's in the next room. I don't care if it's in the next building. This connection into the system needs to be on the inlet side of the circulator. Now you're going to come across jobs where you might have 20 circulators and say, okay, I got all these circulators. Where do I put? There is always a best spot, and we'll get into that in another session on where to determine the best spot. So over on this drawing here, I move that circulator to the discharge, and now I plug that circulator and it says, well, wait a second, I can't change that pressure right there. I can't add water into there. Where would I get it from? I can't subtract water out of there. Where would it come from? Since I can't change the pressure right there, I'm going to make my differential from the suction side of my circulator. So in this case, I put 5 pounds of pressure in there, and my suction, I'm going to maybe take a 6 pound pressure differential, and it takes it from the suction side. And here's what happens. So I'm getting away with it here. I still got a little positive pressure. I got a little bit here, but about halfway around this circuit, I'm down to 0 PSI on that gauge. If you had a gauge on this building and you're pumping at that expansion tank, it gets worse. As I come around here, look what I've got going on here. I've got a subatmospheric, I've got a vacuum in my system in this circuit right here from probably about this point, halfway around that circuit all the way down. So guess what? If this was an auto type of flow type of air vent, What do you think is going to happen every time the circulator kicks on and I pull a negative pressure on that air vent? It's going to suck that float down. It's going to get a gulp of air in there until the fluid comes back around and raises it up. Every time it starts, gulp of air, gulp of air. So over the course of weeks or months or years, whatever it might take, I've got an air problem again. And I can't understand why that's going on. And all you have to do is just move that expansion tank connection to the suction side here. And immediately you're going to get this, this is what's going to go on. You're going to raise all the pressure in your system. Now, if I've got a boiler with a high pressure drop, I'm going to want to put that boiler on this side. So this positive pressure shows up in my boiler. If you've got a low pressure drop boiler like a cast iron boiler, not as critical, but most of the new high pressure drop boilers want you pumping into them. So this pressure increase gets shown up in the heat exchanger, keeps it from flashing the steam in there. Make sure that the pressure switch on that boiler is always being made because I've got that extra positive pressure from my pump differential going in it. So one of the best things you could do with a problematic air job is look at that expansion tank relationship and correct it. And the other way that you fix that, like I just talked about, is putting that anti-siphon cap that we make on that air vent. So if this was an air vent that was seeing that condition and I had that check valve cap on it, I won't get that air in it. Now I haven't fixed the problem, which is this relationship right here, but I've solved that that ongoing air problem. 7-4, yeah, we're doing pretty good here on time. All right, there's another thing that happens in a hydronic system, and it's called cavitation. Some of you guys have heard this term. Usually you'll hear it in regards to a pump, when a pump cavitates. And what is cavitation? What does it mean? Well, I like to think of cavitation comes from the root word cavity. And what is a cavity? Well, a cavity could be a hole in your tooth. Well, cavitation is a hole in water. It's actually a vapor pocket, and it can form in a system, in a pipe, actually. I'll show you how it can form in a pipe. If I've got a low pressure, if I drop the pressure at the eye of this impeller below the vapor pressure, whatever the fluid's in there, if it's water, if it's glycol, it's going to have a vapor pressure which changes with temperature. And if I drop below that pressure, I form these little bubbles in here, and they're not really an air bubble. They're actually a vapor pocket. And what happens to those when they get out through the impeller, they collapse. And when that vapor pocket, this cavitation bubble, let's call it, collapses, it develops a really strong, actually a supersonic speed force right between the bubbles, and it's almost like you've got a sandblaster going on inside your system. Usually you can tell this by the sound the pump is making. You'll hear it, it's like it's got Rice Krispies or it's got gravel in there. You think there's rocks going through the circulator, when in fact what you're hearing is all these cavitation bubbles imploding. They're actually imploding, kind of like when you take an old vacuum tube and break it with a hammer and the glass gets sucked in. It's an implosion, and it's a very aggressive force. And here's a couple impellers that have actually been damaged by cavitation. And this can happen in a few months' time with a big pump if you've got this going on from the day you put it in there. The way you fix that is you got to get more positive pressure on this pump to get out of this condition where I'm getting down to a subatmospheric condition, dropping down below my vapor pressure of whatever fluid, the water that's in there, the cavitation goes away. Usually it's just a matter of increasing your fill pressure a little bit. It's also where you're going to see this is on those outdoor wood furnaces that are open systems. There's very little pressure on the circulator. They're running 190, sometimes 212 degrees when people boil them over. Those circulators are really prone to cavitating because they're in the worst spot possible. They're at the highest temperature, they're at the lowest pressure on the system, and this can happen to those circulators from the day you put it in until a year later when that circulator dies. And that's what's happening, is you're forming these little vapor pockets, and it's going to destroy that impeller in there.
Hey, Bob, we have a good question. This is Kevin.
Right.
A question is, then you were just talking about the location of the expansion tank, and the question is, why is the reason some schematics show air elimination device on the connection point of the expansion tank, which normally is the colder side or the return side of the system?
Yeah, so we're going to get to that. And you know, the expansion tank doesn't need to be on the air purger. Just because we put a convenience port on the purger, the expansion tank needs to be at the hottest point in the system. It needs to be right at the discharge of the boiler. Now, that may or may not be the best place for the expansion tank. If you've got your circulator pump either in the boiler itself or you're pumping into the boiler, I want to move that expansion tank down wherever my circulator is. I mean, a lot of the combi boilers have circulators built right into them. I need to have my expansion tank down by that circulator on the return to that boiler. I don't want to screw my expansion tank in the air vent. The expansion tank really doesn't have anything to do with the air vent other than it's a convenient place to put it. Some cases it might be okay to have it there, but you don't necessarily want your expansion tank in the port on your air purger. It might not be the best place to have that located, and it certainly doesn't need to be under the air purger for any air elimination feature. It's just there because, again, that's a convenient port. I think that I'll clear that up when I get to another slide a little bit more too. All right, where was I? Now, cavitation, let me talk a little bit more about that, because cavitation can actually happen in a piping circuit. It doesn't have to be related to just the circulator pump. And where it can happen, if you put a tight, small restriction in a pipe, what happens, I don't know if you can see these pressure gauges very well, is when water goes through a tight restriction, you get a really high velocity increase. So let's look at that in the schematic over here first. So there's my pressure, and when I squeeze it down through a tight opening, what I'm gonna get is I'm gonna get a velocity increase. Just like you take your garden hose and you put your finger over the end of the garden hose and you get it to squirt a lot further because you've restricted that flow and you're increasing the velocity and you squirt a long way. So in this diagram right here, by squeezing down that hose or pipe or whatever it might be, my velocity goes up. But look at what happens to my vapor pressure. I get down this area right here, and that's where I can get that cavitation forming. So it forms here, and that's where it collapses when it comes through this restriction, which is what I'm showing right up here, a pipe that's been kinked off. And I get that restriction, and that's where you're going to hear that crackling noise. In fact, if you go out in the yard this summer and pick up your garden hose when it's running full speed and take it and just start kinking, and you're going to get to a point where there's just a very little opening, and you're going to hear that Rice Krispie sound. You're going to cavitate right in your hose. So it doesn't have to be in a pump. And where this can happen is somebody's put a globe valve or ball valve in here and they shut it off to isolate a component to work on it, and they go to turn it back on and the handle breaks off or the stem breaks off on that globe valve, and it just opened a little bit, and you don't realize that valve just has a tiny little window. And from that day forward, you've got the potential to form these little cavitation, and it's going to sound like you've got an air problem in the system, when in fact you're cavitating because you got a restriction in a balancing valve that somebody's choked way down, or somebody's kinked a piece of PEX tubing when they put it in the wall, and now you've got that little restriction in there. That noise that you hear is the cavitation forming in there, and it can get worse. This is the Glen Canyon Dam in the Utah-Arizona border. This is a 40-foot diameter concrete pipe, 10 feet thick wall, reinforced concrete, and it cavitated to a point that it actually wore half of this tubing out, and it started chewing into the bank on the side of that dam, and they almost lost the Glen Canyon Dam in 1983 when all this high water was coming down through this pipe at, I ran the calculations on this. If anybody wanted to take a guess how many gallons per minute goes through a 40-foot diameter pipe when it has full velocity like that, I think it comes up to 53 million gallons a minute was going through that pipe. And there were some rough surfaces in that pipe that was causing that cavitation, and it actually eroded in a couple days' time when they were spilling these spillways at full speed when that high water year happened. And then they had to get back in there and rebuild these piping sections with concrete and built that 40-foot diameter tube back up. So it can be a pretty destructive force. As you can see, it's something catch-22 about these internal checks. You know, I like the idea that the pump people stepped up and said, listen, you guys need check valves on your circulators. Let us help you out. I don't like a check valve in a circulator like that. Number one, it's too close to a turbulent condition and they can chatter sometimes. But if you put them vertically like this, what can happen over the summer, if you've got little air bubbles that were trapped in there, they can come up to this check and not make their way through. And you go to start this pump up in the fall for the heating season, and now you've got an airlock pump because all these air bubbles got trapped into the volute. So, you know, in a perfect world, I'd like to see a check valve about 8 pipe diameters away from the discharge. But, you know, maybe it's the lesser of two evils. It's fixing a lot of problems we had with ghost flow. But if you do have a problem with a circulator airlocking a lot, it could be that little check valve is keeping the air in there. Now, ideally, I'd like to get that air out of there and that would go away. But some of the older systems with these type of air vents, you never get all the air out of a system with this type of scoop. It just can't happen. It's physically impossible for this type of device to catch and stop these little microbubbles and get them to go up to this condition right here. Really, all this is a wide spot in the road, and when fluid comes in and it sees, let's say it's coming in here at 4 feet per second, and it sees a wide spot in the road, it slows down just for a second or two as it goes through this device, and that's the mechanism that's making the air bubbles go up to this little vent in the top of it. Now, some of them put vanes in there, some of them put a little ramp in there trying to get the air bubbles to get coaxed up to that, but there's really nothing in here that causes these little bubbles to stop, to, you know, come together and go to the top. That being said, if we would have taken this device years ago and put a piece of screen door screen or something in here, these little bubbles would have grabbed onto that and we would have what we have today, which is a micro bubble resorber. All right, so here's a little solubility. You can find these online. Basically what we're showing here is the temperature of a fluid here and the pressure of the fluid here and the solubility of water or air in water. And the very best place to always get air out of solution is going to be at the hottest point in the system. So let's say we're running at these temperatures up here. So the hottest point in your boiler is going to be right at the boiler. So that's where I'm saying always put the air vent here. Now here I could have the expansion tank on the return side of this. This pump is seeing the point of no pressure change through this big wide open boiler, even though it's a couple feet away from it. This still is establishing the point of no pressure change through the pipe, through the boiler, through the piping up to this circulator. So I am going to see that pressure increase. Now the next best place to get air out of the system is going to be the lowest pressure point in the system, and the lowest point of pressure in the system is always going to be the highest point. So if I've got a manifold or an air handler or a cast iron radiator up on the top floor of my building, I want to have a little air vent up there. Maybe it's just a manual air vent, but a flow type of vent, it's going to keep working for you. So as this air comes out of solution at that low pressure point and at the high pressure, this is going to do 99% of my air removal. This is going to catch air that rises up when the system goes off or any air bubbles that are formed when you change the water, something like that. But they really do work in conjunction with one another. I think that might have helped with the question that Wheels had. And so here's what it is. So what we know is if we take water from 50 to 195 degrees, and let's say I've got 100 gallons of water in the system, that just raising that temperature across that range there from 50 to 195, 140 degrees there, 2 gallons of air is going to come out of solution. So you better have a device, you better have an air vent that's got the ability to get that air out of there. Otherwise, it's going to keep going around in your system and ever causing problems. The other thing that can cause this to happen, this air to come out of solution at that kind of amount, is the pressure. If I could take the pressure of that fluid up, you can see the same thing happens there. I'm going to get about 11 gallons of air out of that system by just dropping that pressure from 75 PSI, dropping it down to atmospheric, which is what, 14.7. So it's both the pressure and the temperature. What I would do on every boiler that I put in is I would take it when I'm standing in front of it and take it up to 190 degrees. Even if you do that only for an hour or 15 minutes, you're going to drive most of the air out of solution that comes out against the wall of that boiler by raising that temperature up. Now, it might do that when it goes in a domestic water call, but at that high temperature is really going to help you get that air out quickly. You won't get it out at the low temperature operation like you can at high temperature. So this is really, I'm going to credit Spirotherm with the first one of these. They said just put something in that chamber and these little bubbles are going to get stuck as they go through there. Different companies use different products. We use a composite media that goes in there and it grabs all those little microbubbles. It does use the velocity decrease by this big chamber in here, but it's really these fingers, these little fine points in there that cause the air to come out of solution and go up to the top of that. I'm getting the hook here from my wife about my time. Sorry, I'm kind of running over. We'd love to help you with whatever air solutions you need. We go all the way up to 14-inch pipe size from 3/4. So if you need something, give us a call. We'd love to help you spec it. All of our air vents are rebuildable. You can take the cap off them. You can get in there. You can clean the needle out. You can replace this cap if you have one that's damaged. So it's a very user-friendly air vent to repair when it's on the job. Fill valves, maybe we'll cover this in another session. A lot of the air elimination comes with your initial fill. You got to have a lot of flow going through your pipes to push the air along with it. If you've got 10,000 feet of radiant tube and you're trying to purge it all at one time, you're going to spend a lot of time trying to get that air out. Break it down into small sections or get a fast fill valve that can put in 5-6 gallons a minute. Bypass your valve if you have to, but the pressure is your friend when it comes to getting air out of the system the very first time you get it going. So in some cases, you might want to get a purge cart with a little bit of a, horsepower here. We've got a 1/2 horsepower pump on this, so we can get you about, 12, 13 gallons a minute out of there. So you can do on a bigger piping system, you can get your flush a lot quicker than depending on your fill valve to do that work for you. Get this book and download it now. Amtro's got this on their website. It used to be a hard copy, now they've got it as a PDF. I learned a lot about air removal, especially these old systems. I know some of you guys see these systems out there still. This is an air management system. There's a difference between an air removal, and I didn't know this until recently. I'll admit it, I didn't know exactly what was going on with these old compression tank systems. And what I mean by air management, I've got to keep air in this tank. If I lose this air bubble by putting an air purger on here and I suck that air out of there over time, I'm going to pop the relief valve on my boiler because now I've got a waterlogged tank. So if you do have a system like that, you've got to have a device that the air that you're taking out of this boiler, out of this piping, can be diverted and goes back up into the top of that tank, and that's my expansion space. There's no bladder, there's no diaphragm, there's no physical separation between the air and the water in here. So you got to maintain that air bubble, which is why we call it an air management. Now, what I could do, I could put a Caleffi disc L right here, and what I would do is take that little tube I just showed you earlier, and I put the tube up into here, because that's really what they're doing with this B&G fitting, is they're just taking the air that's coming out of solution here through this little Venturi type of fitting and putting the air back into my expansion tank here. I've got my water, my air separated in here. Some guys love these tanks. You can still buy this tank. They do a good job. There is a lot of heat loss from a tank like that because it's just bare metal. I'll tell you, if you do replace this with a diaphragm tank, it's going to be about 1/3 the size of that, because just the process of putting a diaphragm between that air bubble and that water that's in that tank, you can reduce the size of it because you're not dependent on the just the water touching the air in this system. So the difference between air management, air removal, is the type of the expansion tank that you have on it, basically. So get that book, read up on it. There's a lot of really good information about sizing expansion tanks and sizing it. So that's what I was saying, is just put an air purger in there, but take the discharge tube and run it up to the tank so that air that you suck out of here is still in there for your expansion space in your compression tank. And there you can see a circulator on the return side pumping at the compression tank. You know what? With these little Bell & Gossett Series 100, a very low head pump, they only develop about 3 or 4 pounds of pressure differential. You could pump in an expansion tank with this type of circulator. What goes wrong with this right here is somebody goes back and they take that old Series 100 out of there and they pick a pump, a 1558, whatever you put in, and now I've got a medium head pump, and now I've got 7, 8 pounds of pressure differential. Now I start having air problems because I'm pumping at my expansion tank with a little bit more pressure than I had with that old flat curve Series 100. All right, I got a couple more slides and we're going to get to my my demo here. Know that we do make, I think we're the only company out now that has a low lead air vent. So if you do have to put an air vent on a domestic water system, it needs to be low lead right now. We can help you with that. All right, so this is a demo. I'm going to do a little video here, and I want to just go over this. So I made this as a little trainer thing. I used to haul this around with me when I had a Sprinter van. So basically, I just took a bunch of clear acrylic tubing, and I made a clear acrylic disc L dirt. This is both an air separator and a dirt separator. I made a couple Grundfos pumps out of clear plastic there that I just put the motors in, and I got some other components here. I've got a quick setter here. I've got a dirt mag that we'll talk about in another session here. I made a clear plastic 4-in-1, SEP4, so that's air, dirt, magnetic removal. And then I got some piping. So I put a little blue glycol just so you could see it a little bit better. So the demo I want to do today is I'm going to take and I'm going to inject air into the system, and I'm going to show you how this little microbubble resorber grabs those little air bubbles as they come around there and how quickly it does that. You're going to be amazed how much difference that you can make by just upgrading your air separation device on. Let me see if I've got a couple other slides here, Mary, before I go. All right, so what I did is on this display behind me, I used 7/8 acrylic tubing. It has a 5/8 inside diameter, that should be, because it's a pretty thick walled pipe. So I just want the Plastic Pipe Institute, by the way, you guys should go over there and snoop around a little bit. They've got a bunch of really good information on any plastic pipe. It could be PEX, PEX LPEX, PERT, but they got a lot of nice calculators over there that you can do a bunch of calculations on it. And this is an example one where you put in all the information and it'll tell you what the flow rates you put in there, and it'll tell you what the flow velocity is going through that pipe. So with the pipe I have, if I take the GPM reading from the quick setter when we get this going, I can convert that into how fast the water is going through that tube. Hydronics, we want to be somewhere between 2 and 4 feet per second velocity. That's a sweet spot. You get over that and you'll see what happens when we get over here. I'm going to run this up to about 6 feet per second. Think of 6 feet, stretch out your arms if you're 6 feet tall. Your wingspan's about 6 feet. Think of water going across that distance every second. That's moving pretty quickly. Hard to get air out of a fluid when it's moving through a pipe or through a separator that quickly. So, all right, let's see what do I have to do here, Mary. That's what it's going to look like.
Do you want to do your last slide with the?
Let me get to my. No, I'm going to do my demo first, and then maybe we'll come back and do. We will come back and do questions, and also do a little bit of housekeeping to end it up. But let me do this. Now, bear in mind that if you don't have a really fast connection, you might, this might be a little jerky. We practiced this at 4 o'clock today with 4 different people, and 3 out of the 4 people it worked perfect. And the other guy said it was kind of jerky. It's not me, it's not us. It happens to be the speed of your connection. All right, so let's, this version right here. Let's see if I can do this right. I'm a rookie at this here. See if this is gonna come up.
Yeah.
No, there I am, my mechanical hub shirt. All right, let's get this going here. This is only a minute and a half, so bear with me here and we'll come back. We'll talk here. Now we're gonna do a live air separation demo on this board that I built over here, and I wanna show you a little bit how it works and how I built this. So this is built with clear acrylic tubing. You can get that from usplastics.com online. They can ship that to you. It is a copper tube size, so you can use grip fittings to put it together if you want. You can glue it also. So inside this here is a Caleffi disc L dirt, and it's built with this composite media, and that's what does the removal, both the air and dirt removal. We'll get this going here in a second. I'll show you how that works. A couple circulator pumps here. I built them in a clear plastic block, so you can see the impeller in there. You can see the air on the impeller. You can see cavitation and just see how the circulator actually works in real life. Then over here, I've got, let me turn this on. I've got a quick setter, Caleffi quick setter, so we can see the flow rate that's going through that. We can translate the flow rate into fluid velocity, feet per second, so we know when we get in that sweet spot, that 2 to 4 feet per second velocity. Coming around here, just my little fill. I do have a little bit of glycol there, the blue, just so it shows up a little bit better. A little tougher to get the air out, but it does, I think, jump up the board a little bit better. Now, if we can move down a little bit, closely spaced tees here. We're not going to talk about this today. That'll be for another session, but that's like closely spaced tees. Then they go down. Flow is going to come across this and go back up. And then we'll see the air removal here. So up at the top here, if you could look at this, this is a little, it's just an aquarium air pump that I bought from PetSmart, and I can inject air into here. I can regulate how much I put in there, and then you'll see how it goes around through the loop I just pointed out, and you'll see it come back here, and you'll see the bubbles come out, and you'll see how air separation works. So if you're ready, let me turn some things on here, get my pump on. I'm gonna put a shot of air in there, and now if you watch when I pull this out, get my flow rate going. Get a little bit more air in there. Now you'll see those air bubbles going around, and then if you put the camera over here, you can see the air coming out, and you see very little. Some of the small bubbles are going to go through. This is going to take about, maybe 5 minutes for that air to go around, and after 5 minutes, you'll see this will be completely free of air here. You'll see all the bubbles will stop coming out. Now, if this was clear water, it happens in about 5 minutes. In fact, almost too quickly to really see it work. But by putting the glycol in here, the viscosity, of course, a little bit thicker, so it gives up its air a little bit slower. So maybe that does work out better for watching it. And I don't know if you can see it on the camera, but see how this water is swirling through here? That's an indication of turbulent flow conditions. It's almost going through like a corkscrew. If you can see that, you can see it when the air bubbles come through, how it winds through there. And that's what you want when you're trying to get heat out of a pipe or heat out of an emitter or something like that. You want turbulent flow conditions. I can slow the circulator down until I drop down below the 2 feet per second, and you can see I can actually get down to where you can barely see the water moving through here, laminar flow, which of course would excuse me, be good for heat transfer. So let me just do another quick one here. Turn the pump off, another shot of air, turn it back on, and you can see the air going around there. And immediately the big bubbles come out, and then the little ones collate on this median side there, the coalescing median there. And again, after about 10 minutes here, you'll see this fluid will be completely blue colored, free from air, dissolved air, entrained air, big air, all the air that we need to get out of our system will come out in the separator after time. This is also going to do dirt in another session. We'll put some dirt and some deposit stuff in here, and we'll watch how the bottom part works. So that's what I've got. Thanks for watching. Let me just do one more here where I really cranked up the flow rate in that. Double click on that.
Yeah, that's right. I haven't seen that one.
Now, different here is I really cranked up the pump speed, and I'm going through there about 6 feet per second. You can see right there, I've got 5.5 gallons per minute. If you look up my chart there, 5.5 gallons a minute. So yeah, right around 6 feet per second. So you can see the water is really racing through there. That's too fast, really, but I wanted to show you how air removal, even if you're running your you can see there how it's kind of swirling through there. And you can see the little micro bubbles coming out of solution there, even at that high speed. So basically, I've turned that circulator into a wearing blender. And there was a song a while ago that said, "Put me through some changes, Lord, sort of like a wearing blender." If you can name the artist or the name of that song, I'm going to give you a free air vent. We'll send it to you. It was 1976 was the year, so that might date me a little bit. But I always remember that wearing blender thing when I think of a circulator pump that's way over pumping the circuit, because that's what you're going to get is just a foamy water like you see going on in there. Now, I will, after a period of time, get those little micro bubbles out of there, even though it's foaming up like that from that high velocity that I'm going through there. But yeah, you don't want to over pump a circuit. It just makes the air removal that much tougher. And just know that glycol is a really stubborn fluid to get the air out of. It takes so much longer than regular water. So let me get this off and get back to my presentation, Mary. And I don't know if you want to do the camera again, but.
Bob, we have got a hand up.
All right, let's do it.
Dennis.
Hi, Dennis.
Hello?
Yeah, we can hear you.
You can hear me?
Yeah.
Are you looking for Poor Poor Pity Me, song by Linda Ronstadt?
That's exactly it. Actually, it was
Congratulations.
Warren Zevon, I think, wrote it, but I think Linda did a better cover of it than Warren did, but that's exactly right. So I don't know if we have your address, but get it to us and I'll send you an air vent with a check valve and a hydroscopic cap. How's that? And I'll throw in a check valve cap for it. I'll give you a 4-in-1. Thanks for playing our game.
No problem.
And Bob, Eric Ani has been very patient with the question, and it is in regards to hygroscopic caps. So he's wondering if the hygroscopic caps can be used on any other brand auto vents.
Yeah, they will. You know, I think most of the air vents out there are metric threads on the top. Like I say, the only one that I found that it won't work on is that old made of the, and I say old made of the mist, but those kind of sheet metal or sheet brass type of air vents, those are made in the US and they've got a kind of a shred, they've got a tire stem cap on it, basically is what they have. But I've tried them on Watts, I've tried them on Taco, I've tried them on some of the Honeywells, but I can't promise they'll work on every single one out there, but every vent that I've seen, you know, it's the same thread and the cap will fit on it. So they're a handy little cap to have. I mean, I put them on, like I say, inside of boilers, anywhere that I'm worried about a vent making a mess someday. It just gives me a little bit extra peace of mind or protection on a vent. What else you got, Mary or Kevin or?
Well, we have another hand up.
All right.
Well, we did. I'm sorry. Sean, did you have a question, or maybe that was false alarm? Kevin, are you seeing any other questions?
I do. I see a question from Andy McGee. How many feet per second do you want to put into a system when trying to remove debris? For example, when you're switching from an old cast iron to a new high efficiency boiler. That's a great question about dirt. Yeah, it is. And so here's what happened. A couple years ago, I was at a Geo Expo in Tulsa, Oklahoma, the IGSPA show down there, and we had a booth set up there, and we were trying to sell some of our air vents and stuff to the Geo people. And a couple of doors away from me was this company out of Texas called Purging. So I get to talking to these guys. I said, well, what do you guys do? He said, well, we go around the US and Canada and we purge out problematic systems. I said, well, why would I need you to do that? Isn't that what I do? And he said, well, a lot of people don't understand that if you've got dirt and debris in an old system or in a Geo loop, and they do big stuff, I'm talking like 4-inch pipe size, they can purge up to 24-inch diameter pipe with these different pumps. And I said, well, what's different about what you do and what I do if I'm trying to purge an old system and get the rust and crap out of it? He said, the velocity. He said, you got to get the pipe velocity up above 5 feet per second. He said, as soon as you hit that number, 5 feet per second, he said, stuff will just come out of the pipe. And he had pictures of stuff they had purged out of old systems. And so what they do is they go into a job and they put these they're like big handcuffs that go around the pipe, and they're ultrasonic flow meters. And he said, what we do is we measure the side of the pipe, size of it, and we put the flow meter, the ultrasonic flow meters around it. And they said, then we go out in the parking lot and rev up and they've got a Turbo Cummins diesel powered pump that can pump that kind of flow out there. He said, we'll rev that up until we know that the flow velocity going through that pipe by measuring the feet per second gets us that 5 feet per second. By measuring the gallons per minute, I mean on the flow meter, they convert that with that little chart I just showed you to feet per second. He said 5 feet per second is the magic number. He said anything above that 5 feet per second, he said sand, he said cell phones and tools and rags and everything else that they purged out of systems. They had all kinds of pictures of what they had taken out of systems over the years. He said that's the number that you have to get up to. So, for you to do that on a job site, you're almost going to need a pump cart.
And, you know, depending on the size of the pipe you're doing, you might need a big pump card. You know, that little half horse, you can probably do up to maybe inch and a quarter. You can get up that kind of flow velocity. But if you're trying to pipe a big job with 1.5 inch, 2, 3 inch, whatever, you're starting to talk about 5, 10 horsepower worth of pump to be able to do that. In fact, the smallest pump that company had was a 5 horsepower. And the biggest one, they had 2, I think he said 160 horsepower Cummins diesel pumps on a big fifth wheel gooseneck trailer that they would haul around when they had to do, you know, large jobs. He showed a job that was in Indiana somewhere. It was a geo loop field that was put under a parking lot, unfortunately, and it never worked from day one properly. And so they figured they had some airlocks and stuff. They were actually 2-inch loop fields, came into a 10-inch header that came into the mechanical room, and they hooked onto that 10-inch header and they purged that thing out. And they had 2 sheets of plywood out in the parking lot that were just heaped to the top with sand they had blown out of that. So apparently they had pushed some tubing under the road and the cap came off, whatever, and they just filled a bunch of that tubing with sand, and it had never worked from the day it was put in there, and it never had enough pumping power to move that fluid along through the system. So it took that kind of a, you know, horsepower and getting that velocity up above that 5 feet per second to make that that dirt particle start moving and coming out of there. So yeah, that's that.
Yeah, thanks, Bob. Another one from Mike. Seems to have issues with air vents and glycol systems over time.
Yeah.
Is there a trick for air valves to last in glycol systems?
Yeah, you know, there's one good thing about glycol, and only one good thing in my mind: it doesn't freeze. Everything else about glycol is just a pain in the butt to work with. You know, it leaks out of O-rings, it leaks out of seals, it leaks out of crimp joints. It's hard to pump. It doesn't exchange heat very well. Yeah, I know what you're saying. I mean, I've seen brand new Pro Press joints leak from the day they were put in because of that fluid. The surface tension of that fluid is so low, it just sneaks out of everywhere. So yeah, you know, we've tried Buna rubber, we tried EPDM, we've tried all different types of seals in our air vents. We think we got a pretty good air vent now in that we use a peroxide cured EPDM on our O-rings, and that seems to be the most stable product that we've found. But if the glycol goes bad and the pH drops or it gets real dirty, it's just, I don't know. I don't have a really good answer. I would say just watch the glycol. The best thing that the guy from Dow Chemical told me about glycol, he said, take a glass and just take a little bit out of the glass. And he said, if it's ugly looking, he said, if it smells real bad, get rid of the glycol. Because he said, number one, the pH is going to be down in the 4, 5, 6 range. It could be acidic, could be really bad. But he said, you can usually tell by looking at it first in the glass if it doesn't have the nice blue color, red, whatever it went in. If it looks like coffee, it's bad. He said if it smells really kind of a harsh, like locker room smell to it, it's bad. So he said most of the time you can tell glycol by looking at it if it's time to get it out of there, because it's going to go after your seals and your O-rings and everything in your system. It's just the way, there isn't really a better fluid out there for antifreeze that we found yet. So, all right. What else?
Hey, Bob, this is John. Would you mind activating your camera again?
Yeah, how do I I thought Mary was going to
Right
toggle me in
there.
and off there.
There you go.
Sorry about that. There I am. Let me get back down here too.
Do you want him to show his shirt?
No, I'd love to see Hot Rod's face when he's talking.
Well, that's what happens when I toggle to the videos. I got to remember to come back to my camera. So I've got a couple housekeeping slides. I mean, I'll stay as long as people have questions if you want to, you know, read them or open their mic. But this is our team. You know, they're working from home, but if you need tech support, we'll help with other brands. If you got a question about an air vent, we don't mind chatting with you and helping a brother or sister out if you have a question or an application question. We do have this Thursday, Mark Etherton is going to talk about commercial boiler retrofits. I do a lot of that at his company out in Denver. So he's going to give us some ideas of tips and tricks that he's learned over the probably 40 years he's been pulling wrenches too. So if you got time this Thursday at noon, tune in for that. You know, we try and keep a presence on all the different sites out there. I mean, it's a full-time job just keeping track of all this these days, but however you guys want to communicate with us, if you want to FaceTime with us from a job site, we can certainly do that and help you out. This is what we've got in mind for the next couple weeks here. We'll keep this going as long as you like it. We're going to talk about dirt and magnetic separation next, and I want to talk about primary secondary. I built behind me that primary secondary tees, and I've learned a lot just by watching how primary secondary works and some of the things that they didn't tell us about primary secondary back in the day that we'll talk about. And then I'm going to talk about the heat transfer, how different type of heat emitters work, how we size them, how we can run them at lower temperatures. So that's kind of what I've got in mind. And I think, yeah, to make a long story long, thanks everybody for hanging out with us tonight. Sorry,
Yeah.
we're a little bit long.
And Bob, before we tune out, I've got some really good news about our charitable donation because of our very cool, awesome audience. I checked the math twice. $895. Well, we'll bump that to $900. So we're going to be splitting that between Chefs for America and Samaritan's Purse. So thank you, audience.
Yeah, thanks everybody.
And the Hub also wanted you to know that if you enjoyed this presentation, they are actually going to be posting this up on their website. So watch for that. You can re-listen or share it with friends. And yeah, stay tuned. We'll be back next Monday.
Yeah, sorry I talk so fast, but I try and get excited about this and get a lot of information, probably more than I, 200 pounds of potatoes and 100-pound bushels, what we used to say back on the farm. So, but thanks for hanging in there with me. And, let us know for topics that if you have some other things in mind, we can certainly, gear up for that pretty quickly and do it. And we're going to try some better technology. I'd like to be able to do a live demo. I don't know how well that's streamed for you folks. Let me know if that came through well enough. It's just a bandwidth issue. I wish there was a simple solution for that, but we're going to keep trying different things until we get this as good as it can be. All right.
You had mentioned that this presentation would be available to people if they want it.
Yeah, I mean, the PowerPoint slides, at the end of this, there'll be a survey if you want to fill it out, and it'll ask you, do you want the presentation? And I think almost instantly, Mary will send the PDF file out to you. And then as far as archiving it, I don't know, John and Eric, how you guys do that on your end, but we have to convert this to a different file. Mary does that somehow from the webinar, and then turn it into a YouTube or however you guys want us to send you that data. We can send you the raw file or whatever you guys need or want. It's yours. I mean, it's yours to use and have for whatever you want.
We appreciate that. Thank you.
Well, thank you guys for presenting this whole concept. This was a great idea, and it couldn't be a better time to do at-home learning. So all the kind of everything came together just right.
Hey Bob, this is Eric. I just want to say thank you, and also just tell you my phone is blowing up on Instagram. I'm getting tons and tons and tons of tags and messages from everybody that's been watching all night. So they said you're doing an awesome job, and they're just super thankful that this training is coming together for everybody at this time. So thank you.
Thanks. Good to hear. All right, I think we'll, Mary, unless there's anything else, Kevin, we'll call it a wrap.
Thanks,
I think
Bob.
it's bedtime. You bet. Thank you, everybody. It was a lot of fun.
Thanks. See ya.
Everyone.
Bye-bye.